Dear colleagues, welcome everyone, both offline and online participants. And today it's our pleasure to have here Professor Moulines from Ecole Polytechnique in Paris to present us very interesting research on distributed and federated learning coupled with Bayesian inference. And yeah, basically, Professor Eric is well-known expert in sampling, in stochastic process, in Monte Carlo Markov chain, and in many various topics. And yeah, I give floor to him.
Thanks a lot. I hope everybody. So it will be your first French lesson because I have a very bad English inherited from my background from the 70s, you know, where it was not very fashionable to learn languages, and I learned Russian as first language. So, so it's a joint work that I have carried out in Lagrange Mathematical Center, which was created by Merwan Debar. So before he left Paris to Abu Dhabi, and so I am involved in the center. And so it's a joint work with Vincent Placier and so Alain Durmus, who is working with me, was a PhD student of mine, and Vincent Placier is also a PhD student of mine. So now Alain is a full professor at Ecole Polytechnique and is also participating to Lagrange. So I will start with a gentle introduction to what I do. So perhaps if I hope not to be too long with this, I will speak about uncertainty quantification. And then I will show 2 or 3 works that we currently do in this direction. So what is uncertainty in AI? So it's a big issue now that because when you do artificial intelligence, what we typically do is that you are willing to make decision. And when you are willing to make decision, of course, you need to somehow to have some measure of confidence of what the machine suggests. So representing uncertainty is certainly critical when you do decision making. So it's a full calibration of error. It's an important problem in statistics, which is so there are many examples like in medical diagnosis, or it's for autonomous driving. So we want to protect under rare but very errors which can be very, very costly. And the thing which has been observed by many researchers recently is that deep learning model especially typically lack a representation of uncertainty. And what has been shown, in fact, or through many examples, is that typically deep learning models are overconfident, okay? So, and are often very badly calibrated. So the accuracy can be very high, but confidence is in general quite poor. And so the objective of this talk is to represent uncertainty and in a way that we can trust. Of course, uncertainty plays an important role in other AI applications, in particular in active learning, but I will not speak about active learning today. Okay, what is the classical approach? The classical approach in machine learning is, of course, you have a training set for supervised learning. So what you do typically is that you have a statistical model. So a statistical model is a way to specify the probability distribution of the label condition to the covariates. And typically this model depends upon many parameters. So it's in deep nets, it will be typically the bias and the synaptic weight. So D can be extremely large. What you do typically is that you do a parameter estimation. So by maximizing the likelihood or minimizing the risk, it depends the way you are looking at the problem. Sometimes you add some kind of penalty, like to avoid leakage. And of course, if you look at a classical machine learning problem, it will give you some idea of it's also an estimator of the predictive distribution, because most machine learning provides some quantity which can be interpreted as a kind of probability. So that's a classical approach, but and I've taken this from an image processing problems, and so you can see there that you have some rare errors, but the rare errors are very difficult and to see, and you will see that this model is very, for example, an example of a model which high accuracy but with which is badly calibrated. So this one, for example, the model recognizes a bird with very high confidence, whereas it's not a bird. So I take some. This is considered as being a mammal, whereas it's a bird or something like that. So it's a typical example where you have a good. It's a very good. In fact, if you don't report the accuracy, but the accuracy is very good. In fact, in this task, but at the same time you have errors, and the system makes error, whereas it's very confident about his decision. So of course, if behind this you have to take a decision, you have to take an action. Of course, that's a big problem. So of course there are some calibration metrics. So we don't spend much time on that because it's a kind of introductory talk. So calibration metrics. So what typically people report. People report log likelihood on test sets. That's a good one. So one which is also very classical to report is to report what is called Brier scores. So typically a Brier scores, you simply compare the decision which has been taken with a true decision, and you compare this with the probability of decision. Of course, if you have a correctly calibrated model, the Brier score should be small. And the quantity which is even more important is what is called the expected calibration error. And the expected calibration error is a kind of, it's a model which makes on test sets, of course, a measure of accuracy. So accuracy is how many times you get an accurate answers with respect to confidence. Okay, so it's accuracy minus confidence. You take the absolute value, and then you do that on a kind of line. So that it's a nice way to look at calibration. So there are many other methods to look at the calibration issue, but that's good criterion. And when you look at classical method are in general very, very badly calibrated. So it's a calibration error. So accuracy is large, but calibration error is bad in general. So the system is badly calibrated. So which means it can. So what typically happens is that we have seen in vision problem is that you can have very high accuracy, which is typical. Very high accuracy is very typical of today machine learning. So super large accuracy. At the same time, is when you make a mistake, he's still very confident. So so the thing that you are willing to see is that sometimes he never says that he's not sure. So accuracy is always large. Okay. So you don't see it's very rare to have something like, okay, so the softmax is 0.6. It never happens. It's always 0.999, and even if it's completely wrong. Okay, so this is why we are willing to look at slightly different problems. Okay, so there are many techniques which have been proposed so far to remove this calibration problem, and one of the approaches, it's not the only one, of course. There are two approaches which have been more or less considered, which are not that different, I would say. The approach by ensembling, some kind of bagging, but a very simple bagging, which is ensembling. So ensembling is typically you run algorithm with different initialization, and instead of looking at one decision, what you typically you look at. So you pull the decision together, or you look at all the decisions which have been taken by the model. The other method, which is also linked with ensembling, which is another way to do ensembling, is by Bayesian approach. Of course, the third method would be dropout. Monte Carlo dropout is also a method. Very difficult to understand, by the way, theoretically. So it works well, but very mysterious somehow. Bayesian approach, at least there is no mystery, so it's not. There are many other issues, but there is no. So you can understand what you are trying to do, or at least you understand a little bit. The objectives at least are clear. So there are a lot of problems which are hidden behind the hood, but the objective at least of Bayesian inference is very clear. Whereas the dropout is less clear. So what are the Bayesian inference in AI promises? So it promises to do improved prediction. It promises to do reliable uncertainty estimate. And also, and I will not discuss that, it's also, in principle, it can be used to model comparisons. Okay. So there is a big community which is called Bayesian neural net. So So if you look at, so if you look on Google Scholar, your best friends when you are doing research, before it was much more complicated. So in Google Scholar, so I did that in June, I think. So you have 10 to the power 5 result when you simply on the word Bayesian deep learning or Bayesian neural net. So it's incredible the number of papers which have appeared in the last 10 years in this topic. And you have many applications which have been considered. So you will find BNN in astrophysics, the automatic diagnostic, diabetic retinopathy, advertising, click-through, rate prediction, fluid dynamics, and things like that. So there are many different applications of Bayesian deep learning. And in fact, Bayesian deep learning, it was the first method which was used and successful in Bayesian approach by Radford Need, so which was there for about at least 10 years or more than that. It was Bayesian deep learning by Radford Need, so it used a Hamiltonian Monte Carlo. It's a very good PhD thesis, by the way. So it's from the 90s, where it was more or less state-of-the-art prediction, and until at the end of 2000, 2008, 2009, it still won a lot of competition for prediction because it was extremely robust and well turned. It was not deep net; it was like shallow network with Bayesian model averaging. So what is Bayesian approach in a nutshell? So very simple. You have a training set. Okay, so you have a statistical model, the same type of statistical model that you use. So typically a deep net. So you specify a probabilistic model of the of y given the covariates, and you add another bit which is a prior distribution. So I will not discuss how to make a prior for deep net. Of course, it's a bit critical there, but I will not have time to explain how to proceed. So you put a prior. So when you have a prior, you define two things. You define first the likelihood of the observation. So typically assuming that the observation are high D, the likelihood of the training set is simply the product of the likelihood of each observation. Okay. Of course, it is challenging because you have typically the number of observations is very large, so the likelihood is a super large number of terms. I will explain later. And then what is the objective? So you have a prior, you have the likelihood. What is the objective of Bayesian inference is to infer the posterior distribution, so the distribution of theta given D. So you apply the Bayes rule, and applying Bayes rule, you simply have to compute the product of the prior multiplied by the likelihood function. And of course, this quantity is defined up to is normalizing constant. So there is a normalizing constant because this is not a probability distribution. So you need to normalize. And of course, the normalizing constant is unknown. This is classical in Bayesian statistics. So you need to have a sampling algorithm, or you need to be able to approximate posterior distribution without knowing the normalizing constant. Okay. So in classical ML, what you obtain one model by, say, minimizing training error or maximizing the likelihood plus some regulation term. What we do in Bayesian ML, you infer a posterior distribution. And typically, what we call Bayesian model averaging, so you compute the posterior distribution, the posterior predictive, so you take a new set, a new observation, yx, and you compute the posterior distribution of y given x and the training set. And this posterior predictive distribution is simply the product of the predictive distribution of y given x for a given value of theta, okay? And then you integrate this quantity formally with respect to the posterior distribution of theta given d. Okay, so that's the principle of Bayesian model average. Of course, you don't implement this like this because you need to compute an integral. Remember that theta is over super large dimensional space, so it's not, you will never do that. So but basically what you do is that you will sample this distribution. So you need to approximate this distribution either by sampling, which I will present today, or doing variational inference. So I will not speak, so I work also in variational inference. So in variational experience, what you do is that you approximate this distribution by another distribution, and you are maximizing something like cross entropy between the true posterior distribution and the variational approximation. Okay, so today I will not discuss this. I will discuss more the problem how you sample basically so you will do a Monte Carlo approximation of this integral. So basically what you will do is that you will form an ensembling. So it's a Bayesian ensemble, if you wish, because you will draw some value of theta, and then you compute, you average, in fact, py given x theta according to this, the samples that you have drawn. Okay. Okay, so there was, if you are interested in this type of result, we don't have time to discuss this, but there was a big competition last year in New Rips in 2021. So my student and the student of Maxime participated, they finished second. So we were very, very angry against us. They need to finish first, okay? They say finish because they work a lot, and it was only okay. So they did quite well on all tasks except one. So we never understood why. So the one task it was complete failure. Otherwise, we will be the first. Okay. So there are other solutions that we not explain. So deep ensembles, they said Laplace approximation. Our guys did SWAG, so Russian invention. So others use MC dropout. So there are many other ways to form ensembles. So all the method in general to do to obtain best calibration error are always around ensembling. So having some copies of. So of course, last year in the New York competition, you had only 100 copy of the network, which is huge. In fact, if you have a large language model, it's typically will not be very happy to have 100 copy of this. So that's already a problem. So you can do also partial ensembling. So instead of having an ensemble with different parameters for all parameters of the model, you can have only some parts which are different, or you can do modulation like Maxime do. So you have other tricks that you can apply in order to reduce the complexity. But typically, what you have to have in mind. So in fact, there is a special taste to what we do there, because the dimension of DeepNet is huge. At the same time, when you do Monte Carlo approximation, you will always take a very small sample. So it's not the classical Bayesian method. Classical Bayesian method, dimension 10, and you draw 10,000 samples. So here, dimension is billions, and you take 100 samples. So it's of course you have dimension r to the power 10 to the power 10, and then you have only 100 samples. It's better than one, but it's not really Monte Carlo in the sense that you cannot pretend that you will fill the space with this type of stuff. Okay, so there is a special flavor behind this, and you need some time to be pragmatic. So in fact, what people use in this type of method for Bayesian neural net, the typical people so it's really related to what people do in classical, I would say, machine learning. So you use only first order methods. The only thing which you are allowed to compute is a gradient of the likelihood function. And around these techniques, there was a proposal which has been proposed by it's a very influential paper which has appeared in New Rips 2011 by Max Welling and Yi Wei-Te. And they proposed to run, yes, the idea was there much before in machine learning, but I think they were the first to apply that to Bayesian neural net, is to use discretization of Langevin diffusion. So just in few words, what is Langevin diffusion? So it's a continuous time process. It's a stochastic differential equation. So it's a Markov process which obeys this equation. So the equation which is like this. So you compute the gradient of the logarithm of the probability of theta t given d. Okay, but this is this quantity, of course, it is a product. So you have two terms there. So it's a product of dt given theta and multiplied by the prior distribution. So it becomes a sum. So this quantity does not depend upon the normalizing constant. So this is fine. And what you can prove is that under conditions which are simple, like local Lipschitzness, and some kind of course, you need some kind of the fact that so when you are far in the tail, you need some force which puts back to the center of, which is typically what this condition says. So basically, you have a form of, so when you are far in the tail, you are going within to the center of the state. And you can prove that this diffusion has a unique invariant distribution, and this unique invariant distribution is precisely P theta t given D. Okay, so if you run the Langevin diffusion, so Langevin diffusion is ergodic under very, very weak condition. So smoothness of the gradient and coercivity. And when you run it for a sufficiently large amount of time, you will converge to the posterior distribution, which is the distribution that you target. So so if you are able to run this diffusion, then you are able to sample from this posterior distribution. Okay. So the idea is very simple. So of course you cannot right now we cannot simulate the continuous time process. Perhaps in the next, so in the future we can do that. But right now what we do, we are still working on sequential computer. So what we do is that we do some kind of discretization. So you use a sequence of step size. Gamma, you can take here, write that with a constant step size. You can use decreasing step size, like in stochastic approximation, exactly the same. You compute the gradient and you use a Euler-Maruyama scheme. So you compute the gradient, and what you is look exactly like a gradient descent algorithm, but you add some noise, okay? And you should be, so if you have gamma there, you should have a noise which is square root of 2 gamma. Okay, so you add some Gaussian noise, and you run problem like this. Okay. So these methods are biased in the sense that what you can prove is that under the condition mentioned earlier, this technique is a Markov chain, so it's no longer a Markov process, it's a Markov chain. You can prove that this Markov chain also has a stationary distribution. The stationary distribution is pi gamma. It's like pi gamma reflects the fact that it's not exactly pi, there is some bias, which is due to the fact that this Markov chain converges to a stationary distribution which is not exactly pi. Okay, and so there are many works which have been done. So I worked a lot on this with Alain. So you can prove that basically it's pi gamma is equal to pi. So the target distribution p theta. So we converge to p theta given d, and the error is of order gamma. If you look at Wasserstein distance or total variation distance, it's the same. It's of order gamma. So you lose a log if you are looking at total variation distance. Okay, so of course it's and we have very precise result if you are interested in that. So you have precise result on mixing time. So you can the mixing time, you have dependence in dimension. I will not speak too much about that. So especially, so it's very, very easy to analyze when you are M strongly convex, and if it's more complicated to analyze when it's not strongly convex, of course. But if it is strongly convex, what you do, you can couple basically the discretization and the diffusion itself, and you can obtain super tight results. So you have the bias term there, it's Wasserstein 2 distance bias term, and then this is transient term, so the way you forget the initial condition, and you have a completely explicit expression for the bias. You can answer also questions like this: how many episodes you should run in order to obtain precision epsilon. So what you should have in mind is that in practice, it's typically much longer to learn diffusion than stochastic gradient descent. So you typically you use in general smaller step size, and you run it much longer than classical stochastic gradient. So if you do 100 episodes for stochastic gradient, you will typically use 10,000 or 10,000 episodes if you are really willing to sample the diffusion. Okay, so that's because you have to have in mind that yes, it looks exactly the same, but at the same time it's slower. Okay. Okay, so of course in the big data limit, the gradient evaluation is complex because so you need to scale like the number of observations. So of course you can replace the full gradient with SGD. Then it's called stochastic gradient Langevin dynamic, which is more or less the most important MCMC algorithm in Bayesian inference for large data sets. So there are some tricks, I will not explain these tricks, but there are some tricks which are important, which are not important in SGD, which are very important in SGLD. So for example, there is the thing which is important if you are really willing to have the right posterior distribution, you need to apply variance reduction techniques. Okay, variance reduction techniques like Saga, SVRG. So perhaps you are familiar with these names. They are never used for deepness. So people use SGD. So you don't reduce the variance of the gradient. If you don't do that, in fact, it works very badly because there is too much noise in the gradient. So there are some. You need to be a little bit careful when it's not simply take your SGD, add noise. It will not work like that. You need to be a little bit more careful. But yes, it's rather simple. There are other methods. You can do HMC, so Hamiltonian Monte Carlo. You can do, so HMC is very popular because there are very, very good software. So called NUTS, perhaps you know NUTS, or I've been using Pyro, so who is Pyro? So nobody use Pyro. Nobody knows. No. So there are very good implementation of HMC. So because it's supported, HMC is supported by Google. So Google support HMC. So they have a very, very good implementation of this. You can do underdamped Langevin. So you can use, there are many techniques or tricks that can be used. I will not explain that. It's not the topic of today. Okay, so I will skip that. And I will go to the main point of my talk, so which is how to adapt this to distributed or federated scenarios. So of course, you are all aware that you have massive data sets. And because you have massive data set, you need so there are two options. So either you're able to take all this data on the central server, or what you will do is that you will distribute data to several workers. So you define local data sets, and of course, with this local data set, you define local loss. So there are two related scenarios, and so which are distributed and federated, which are a bit different. So in distributed, typically you have the data and you split them among workers. So it's like there is a central authority which distributes the data, so which is typical of distributed computing. And in federated, it's a different idea. So in federated computing, the difference stems from the fact that the data are collected by the agents, and there are privacy issues. So you never upload the data to central authority. So you keep your data. Okay, so the data remain private. Okay. And the other thing, so you have privacy issues, which are not there in distributed. I will not speak about that. It's interesting, so because you can apply differential privacy and things like this, but I will not discuss these points. And also you have communication constraints. So the data by the agents are privately owned. Okay. The agents act on communication networks, so the links of the networks are not always good. So you can have bad. Sometimes the communication link are not of good quality. So typically you will not exchange data at that time. So you are not always available. You don't have. So perhaps sometimes you have battery problems, so you will not update you. So one of the applications, just to get a feeling of the application, we are discussing with the telecom team is the application where you do federated. I learned that this morning. So you do federated learning where you capture video with you have a car, you capture video. Okay, so you will not, of course, upload the video on the central servers. That would be really too much. And when the car is parked, then you have a GPU and you can update the vision model when you are doing your parking using the data that you just have collected. So typically, they say you collect 1 week of data and then you drop them, and you will update your vision model during this data while this is typical of federated learning. So it means that you will never upload all the images collected by camera in a car to a central server. You will use your data locally to update the parameter of your model. Okay, so this is a typical application. So what you will do, so you have in a single machine, you have a global loss, if you wish, or log likelihood, or minus log likelihood, negated likelihood. On a multiple machine, you have simply the global loss now is the sum of loss. So B will be the number of agents which are participating to the federation. So you have a local posterior distribution, and the local posterior distribution is pi of theta given di. Okay. And so the objective is to sample from this you want to sample parameter theta from the global posterior, and the global posterior, assuming that the data are independent, is equal to the product of the local posterior, okay, which is so you should look that in the loss constant is exponential minus the loss on each local Bayesian. Okay, so I will look at two algorithms which have different flavor, and if I have time, I will describe three, but I think I will not have time. So I will first describe QLSD. So QLSD is quantized Langevin dynamic and with application to Bayesian federated learning. So it's a paper which has appeared last year in New Rips, with written by Vincent Placier, and so Masha is speaking. And so as I said, it's federated learning. So you have data privacy, communication constraints, and different data distribution on each client. We'll answer Masha. Проверить. Никогда. Okay. Ah, it doesn't work. What happened? What do you do?
Select the window.
Okay, sorry. Okay, Masha is back. What is you? Yeah, Camille, so those watch Camille, she is working with girls on Friday. Is it okay, Maxime?
I will meet
Okay, so you have the server. So don't forget, on Friday, Divochki. Okay, so you have the server. So you have this local data, okay, which are on the edges. You have a central authority. So there are several flavors also in federated learning. So federated learning, you have different settings. So I look at the setting where you have a central authority. So you have local data in the central authority, which is coordinating the agents. Of course, there are other settings where it's federated, but with several local authorities which by themselves collaborate, which will be typical of what will happen in 6G. You will not have a huge authority, worldwide authority, which is coordinating all the users at the world level. So you need to be something like there will be a hierarchy of authority. So here, look at the problem when you have a single authority and you have several local data. So what is the difference with distributed computing? So first, the data are not ID. So typically they might be independent, but each local user sees own data. Okay, so and you have the data distribution is not exactly the same. So if you are in Moscow, you don't see exactly the same scene that in Abu Dhabi. Okay, so in France it looks a bit like Abu Dhabi now, but it's very, very hot. But Moscow is never very hot, so it can be very cold. So Moscow during winter time and Abu Dhabi summertime, it's not the same distribution. So that's very important in the sense that you might have a federation of users which have covariate shifts. So it's not like when you do distributed computing, what you do is that typically you shuffle the data. In distributed MCMC, you shuffle the data and then you put the data are the same on each computer. Whereas here, because the data are acquired by each user and each user do not see exactly the same thing, you have what is called statistical heterogeneity. You have also unbalanced data in the sense that some users have a lot of data, for example, or a lot of interesting data, or you have users which are few data or data which are very noisy and which have much less information upon the parameters that you are willing to learn. The data are typically massively distributed, so you can have, so in some federated application, you have billions or millions of users. So I don't run, sorry. So typically in the example I will show, it's more or less like in the order of thousands, but it's massively distributed. And you have communication bottleneck, and communication bottleneck it's linked with what we call partial participation. So it means that every user is not participating to the federation at each episode. So some user can participate a lot, some users are participated only from time to time. Okay, so how it works, it's simple. So when you have a global server coordinating the stuff, so what you will do, so you have the server, so what the server does, so the server gives distribute the parameter. So you can imagine that the parameter broadcasts the parameter. So sometimes with encoding. So here I did not assume that we have encoding in the downlink. It broadcasts to all the user the parameter. Okay. So these parameters are then received by the local user. The local user makes some updates. So the local user makes some local computation. Okay. And when this computation is done, what they do, they upload some information to the central server. So it's exactly the way it proceeds. So you have two algorithms which are very popular, which are more or less the two algorithms have been proposed by Google guys. So the first one is called federated averaging. So for classical case, federated averaging, you see what you do is very, very simple, it's trivial. So what you do is that you are running stochastic gradient on each of the you have some rounds of stochastic gradient on each of the worker. So that's what the local application is doing, and then you broadcast back the parameter theta. So you see, and what is the central authority is doing. So sometimes it can be a bit more subtle, but it's not in general. It's not very subtle. What they do, they simply average it gives the update is to average the theta. So of course it's a bit stupid because there are some very good agents which make a very clever updates. You have very bad agents which are doing bad updates, and you average all these things. So you have many methods to try to avoid this type of stuff, but that basically is the flavor of federated averaging. And the other algorithm, which is QSGD, so it's the year after, it's the same year in fact, but it's a one conference. So this one is New Rips, and this one was ICML. So Alistar, the same from Google. So what they do, they simply what the agents are doing is that they're simply computing gradients. So each agent, instead of updating the parameter itself, compute a gradient. Okay. And then backup, they send the gradient to the local, to the authority. And of course, because you do that, so you cannot compute you don't update the parameter. So typically you guess the parameter, you compute the gradient of your data, and there are much more communication around, of course. So you need to compress the data information. So you use a compression of the data information. So in QSGD, typically you really take into account the fact that you should compress the data, and then you have to use a compressor. So what you do typically, so the technique, so there are many analyses. There is a guy which is working. So you take, you go through the desert. Okay, you go to Kaust, and there is a team there. They are doing all this type of stuff. There are hundreds of papers. Okay, sometimes it's even difficult. What are the difference between the paper? They have a lot of Russian like here, perhaps more. So they are everywhere, and all the paper have the name of the girlfriend of the PhD student. It's Marina, Diana. So you know their girlfriend. So when they meet them, it's okay. And it's so super. So it's not a big gift that they give to the students. Not big gift for the girls because it's so subtle. Sometimes you don't really understand what is the difference between Marina and Diana. Very subtle. It's like, okay, small tricks. So you have, this time you have added some loop. Okay. But what you do typically is that you use a random compression.
You know what group he's talking about.
Gorbunov. Ristarik, Gorbunov.
But there are many Russian PhDs.
Yeah. And so they use random compression. So random compression. So you can use both. You can use non-random. So random compression is very strange somehow because it's not. I never used random compression before. So I am 60 years old almost, and I never used random compression before. So but it's very important in the analysis. I'm not sure it's so important in practice, but for the analysis, it's very important. So what is random compression? So you have the full quality data, you have the compressor. The compressor, of course, produce D bits, okay, instead of, so here it's like 1 bit. So you compress all of the coefficients are compressed on 1 bit only, okay. And you do that in such a way that the expectation is random. So in the sense that if you give X, C is random. So C of X is unbiased. And it's important when you do federated for reason I will not explain, but it's important when you do the unbiasedness is important. So if you are really interested in the fact, so in fact, Richter recently said, oh no, we can avoid that, and we have, you can avoid that, but you are strongly convex for the assumption which are never met, so it's like strongly convex and things like that. Otherwise, it's important to be unbiased, and then you have, of course, you have some fluctuation, C of x minus x to the square is less than some omega times x squared. So it should be like proportional. So which means that if x is small, in fact, the compressors typically should be, the error should be controlled. So relative error, the relative compression error in expectation could be controlled by some omega in terms of variance. So there are methods to do that. So it's easy to understand when you do scalar quantization. It's easy to do because what you do typically when you have a scalar quantizer, normally I have Blackboard, but when you have a scalar quantizer, but instead of, so when you take x, you have level, quantization level. What you do, you take the closest point. When you want to be unbiased, what you do is you take the closest point with some probability. So you look at the points. So you are in the interval, the quantification interval, and then you go to the right or to the left with some probability in order to be unbiased. So it's not very difficult. And what we did, I'm not sure that I explained that, we extend that to, if you're interested in a very good paper that I've written, which has been rejected from URIPS and ISTAT, too bad, but the paper is not bad. It's interesting. We do that for vector quantization. We have a way to do vector quantization and with Voronoi, which is unbiased. It's interesting because in the sense that you can go, we prove, for example, we use ImageNet, so we use a quantizer which less than 1 bit per coefficient. So in fact, which means that when you use QSGD, you can use very quantization with even less than 1 bit per coefficient. So it's the compression can be very high. Okay, so what is QSGD? So QSGD, what you do, as I said, you send. So you have the authorities send theta k, the current estimate, so broadcast, no coding. Each local clients compute a gradient, okay, apply the compressor, and then you send this compressed version to the central server. The central server computes the average of the compressed gradient and then makes the update, okay? So of course, there is something which is a bit strange in the sense that because of heterogeneity, of course, the gradient for each, so the theta k, in fact, typically you expect that it will it's zero for theta star, so the sum of the gradient are zero, but of course this is not zero, okay, because on each local, so the global parameter for each local data set is not necessarily good, so which means that the compressed gradient, if you do that, have a lot of noise, okay. Even when you are near convergence, because every time you compute the gradient of each local blocks is not zero. So you do compression. So this is why there is some trick, and the trick is, in fact, has been invented by Horvath, so Richter team, and they use what is called a memory term. So it has been proposed before. So it's very classical for in scalar compression, so it's called IDPCM, so it's exactly this type of stuff. So what you do is you have a memory term. So each device keep a memory term, which is called eta ki. Instead of sending the gradient, the estimate of the gradient itself, you compute the difference between the local gradient and the local memory term. Okay, and what you prove is that, of course, this memory term will more or less predict this quantity, which means that this quantity is much smaller than this one. And because you have assumed that the relative error, the relative quantization error is bounded in expectation, at least in variance, the relative variance of the quantization error is bounded, this quantity will be much smaller than this one. And so the algorithm typically do the following thing. So the same stuff, so that each client receive theta k at iteration k, compress, send this version, okay, and then update eta k plus 1, okay, it compress this memory term with, you need a leakage factor alpha, otherwise it doesn't converge. But these are local, these quantities are not updated on the side of the central server. But if you look, in fact, the update of this quantity can be done only with quantity which has been which has been sent to the server. So which means that it's exactly like in a adaptive DPCM, which means that you can update, you can make the same computation provided there is no transmission error. Of course, you can update, in fact, this quantity on the central server. So this is exactly what is meant there. So which means that eta ki, of course, is kept on the local client and is recomputed on the central server. Okay. So there is no need to compute these local gradients to send them. At the same time, you improve a lot the quantity. Okay. Okay. So what we do, in fact, you can adapt that to local to Langevin algorithm. So what we typically do. So with local Langevin algorithm, what we do is that we are using mini batch. Okay. To avoid computational cost. We have problem with communication constraints, so we are using mini batch plus some compression, and it works for communication constraint. Okay, so I will describe quickly. So that's QLSD sharp. So I will skip because it's I will look at this algorithm the best. Okay, so let us start with this algorithm. Okay, so let us start with algorithm 2. So that's the simplest one with no memory term. So you simply compute the gradient of the local server, you apply the compression operator, you update the gradient on the central server, and then you add some amount of noise. So it's QSGD, and simply you add this square root of 2 gamma term. And if you can do a theoretical analysis, this is what we have done with Vincent. So assuming, so under very strong condition, of course, so assuming that you have M strongly convex and L Lipschitz, and you assume that you have an unbiased compression operator with this relative, the variance of the relative error is bounded, and you assume some kind of what is called co-coercivity. So it's co-coercivity, is not on the average, it's a co-coercivity which is on each of the potential, okay? And then you obtain, so it's too bad that I have this quantity, this bar there, but yes, I think, remove it, but and you observe that you have the same type of stuff. So you have the Wasserstein term, which reflects the initial condition, which is forgotten at a kind of exponential rate. Of course, if you take gamma sufficiently large, and then you have quantity, which is a bias term with gamma times B gamma sharp. And then you have another quantity, which also is forgotten at an exponential rate with this K minus 1. Okay, so that's, so which means that you, at the end of the day, typically you have the Wasserstein distance is bounded by gamma B gamma square because the two other terms vanish. There is a problem with this technique. Is that the problem with this technique is that the problem with this technique. So if you look at the different terms, so gamma B gamma is linked with heterogeneity and discretization error, and the second term is due to mini batch and compression operator. Okay. So the sketch of proof I will skip. What you can do, the problem there is that you have so in general you take gamma, which is inversely proportional to the total number of data, and the thing is that when gamma goes to 0, this quantity doesn't go to 0, so you have a problem, and this is linked with the fact that with this type of technique you have the quantization error remains is not lower bounded, doesn't go to 0. So you need to do two things. You need to do a variance reduction schemes, okay? So you need to do a variance reduction on the gradients, okay? And you need to do obtain and to add. You need to add also to add a control variate. So it's typically what you have to do. So you have two techniques. So variance reduction. And variance reduction is important for SGLD, and at the same time you should use also control variates. Okay, so I will skip a little bit because it's a bit long. Okay, a lot of details there, but if you keep the idea, it's important. So at the end of the day, so we have this. We have an algorithm, so it's a bit more complicated. So an algorithm, then you have local gradient. You have, it's a bit like a SGLD. like SVRG, so stochastic variance reduction. So the variance reduction for the gradients, that's for stochastic gradient variance reduction. Then you have the memory term, and then you have HKI, which is another variance reduction tip. So you need to mix a little bit the ID. So you do variance reduction and use also these local variates to avoid the quantization error. And at the end of the day, you obtain whatever you want. So you obtain more or less you obtain with control variates with variance reduction, you control heterogeneity. With control variates, you fix a bias problem, and with this local control variates, you fix the quantization problem. So which means that at the end of the day, the bias really goes to zero when gamma goes to zero. Okay, so you end up with something which is cool, and so you have zero bias, a bit like for the classical SGLD. Okay, so that's the type of very small data that we have tried. So it's a mist, I think, if I'm not well. And so what you do, you distribute the way to perform. So very, very simple experiment is to take any data set like CIFAR or MNIST, and you distribute the label very unevenly. Okay, so you put, so some clients at all the 9, some clients are all the 5, and so you do something like this. So in order to simulate the heterogeneity, so heterogeneity is very important there. And we have this result. So if you look at our best algorithm is this one, okay? QLSD plus PP, okay? And which is like better on every stuff, you know? It's like it has better calibration errors, the accuracy is like, but it's accuracy NIST at the same time. So NIST, you are very impressed by NIST? I'm not impressed, but look at TCE, BS, so it's okay. Bayer score is okay, NLL is score, so it's okay. So it works quite well. Okay. Much better than the standard SGLD. It's more or less on par with the SGLD, which is run on a single client. So basically, you can move to, you take SGLD, you distribute it on 20, I think it's 20 clients. You use the SGLD and you don't lose, so you lose a little bit in ECE, not much, okay? And you use a little bit on BS. Well, I think it's this one the best. It should be this one. No, this one is better. Okay. So you don't lose on Bayer score. Your NLL is a bit worse, of course. And look, but if you look at so the interesting thing is to look at the number of iterations. The number of iterations need to be large. So you need to look. So in fact, typically, the number of epochs is large. So you lose a bit in terms of the number of because of the communication error. You need to use a lot of. So you have to increase the burning. You have to increase the training, the number of training periods. So you have to take that into account. And that's other techniques we compare with other techniques which have been proposed so far, which are working, okay, not so well. So what we have done, but I will not have time to explain. So we have also something which is related to federated averaging. So we have the same type of result for federated averaging and the same type of ID. So you need to apply, you need to have these control variates, you need to be careful with variance reduction and things like that. So it's basically the same philosophy for control variates. Okay. So we have also out of distribution. So we prove that if you are interested, I will not spend too much time because I want to have time to explain the second algorithm. So we have a reasonably good algorithm to detect out of distribution results. And so the idea is simply, so what you are willing to do is that you are willing to, so you train on NIST and you put images from fashion NIST and you see whether they are rejected or recognized as a number. So here it's clear that it's easy to see that they are, with this technique, it's called, they reject really this as a technique and method. So the second type of method is in fact, it's not in chronological order. It's the first thing I've done with Maxime Bonneau. So Maxime Bonneau was a postdoc at Lagrange. so founded by Merwan in his previous life. Thanks, Merwan, again, and Vincent Placier. And so it was the first work we did on this in this direction. And it's called DGLMC, so it's also Langevin Monte Carlo, and but it's a different type of technique, and I think it's interesting. Also, if you are interested in federated learning, it looks a little bit like DITO or something like that. If you don't know, so it's a technique which looks a bit like a method which has been used to do personalized federated learning. It's not exactly this, but it looks a bit the same type of flavor. So what you do is the following thing. So same problem basically, but what you will do is that you will look at this problem as a graphical model. So it's where you will introduce local parameters to each data set. So what you have a global parameter, which is often called the herding parameter. So it's like the parameter which will guide all the parameters. And then for each users, you have a kind of local parameter. So you have local parameter for one, for user I, for user B. Okay. So which means that you have each user has a different local parameter, and all these parameters are constrained. So you have a hierarchy. So each parameter are constrained by a global parameter theta, and this global parameter theta makes the local parameter look the same. So the objective there is that you want to so what you want the ZI be close to theta, because theta is supposed to be the parameter which fits in fact the federation, but it's like personalized in the sense that you have each user has also a local parameter. And the relation with personalization. And what you will do is that you will update. So what you will do is that each worker will update his local parameter using his local data. Then we send the result to the global server, and the global server will update in turn theta. If you look at the structure of the model, in fact, the update is very simple. Okay, if you look at the model, the update is very simple. What you do is the following. So you have the posterior, so pi theta given di. Okay, so which is you put a prior on the fraction of the prior which is put. So you have a prior. So like in all Bayesian analysis, you have a prior for theta. So that's the prior distribution for theta. Then you have the local likelihood. So it's a fraction of prior which is given to each user, and the local likelihood, in fact, is written like that. So you have this Gaussian term G rho I of Zi theta, which ensures that this term is so you put a kind of meta prior on Zi in theta. So Zi in theta. So what does it mean? It means that you penalize Zi when it deviates from theta. It's a Gaussian. So it's a Gaussian. This is Gaussian distribution with mean theta and variance, which is rho I. Okay, so typically you don't estimate rho I, so you take rho I quite small. You can make we did not do that, but of course you could have learn also the rho I. Okay, so this really looks like prox Fed prox. It's really related to this. So in the sense that you have a global parameter, you have local parameter, you have a term there which makes that all the local parameters should be close to the global parameter. And on the top of that, you have a fraction of prior, which is given to each user. Okay. So this is described here. So which means that once you have fixed this rho, so what you will sample? You will sample the joint distribution of theta and all the z, so all the local parameters given all the data set. And this is given by this big product. So you have a big product. This is a product of the local posterior, okay, and the global posterior is equal to the product of the local posterior. Okay, so when you do this, so in fact in this case, so you have it's not very difficult to guess what will happen. So the update is very simple. Why the update is very simple? Because of the structure of the structure of the model. is such that when you at step t, when you update the parameter zit, okay, given the parameter theta, you simply so you send theta t minus 1, then you update locally the parameter zi by drawing from this distribution, at least approximately. Okay, so you will typically run a Langevin diffusion on this local distribution. And what is done on the central server is a consensus step. So it's a consensus in the sense that the local server never sees the data. He only sees the parameter zi, the local parameter, and he makes a consensus by solving. So the PI should be there. It solves this consensus step without looking at the data. So at the global server, you simply need to look at the parameter, at the local parameter zi, and you simply update this, and this is completely explicit. In fact, it's a Gaussian. Since everything is Gaussian, so there is no approximation there. You see, the posterior distribution is also Gaussian, provided that pi theta is Gaussian, and so the update formula are completely explicit. Okay, so the only one step is complicated there. The only step which is complicated there is a step which is done on each local worker when you have to update. So you have to sample basically from this distribution. And at each, so it seems to be a bit complicated because it's non-trivial. It's a non-trivial distribution. And at each time step, theta t changes. Okay, so what you do there is that you will typically do a certain number of Langevin steps to sample from this distribution. And if you look at the structure of Langevin, so you will perform ni Langevin local steps on each local server. And so it's a classical Langevin. And because of the Erding parameter, you have a gamma I. So gamma I will be the step size in the Langevin discretization, and you have an additional term which is not classical, which is this one. And this additional term reflects in fact the fact that you need to be close to one parameter which is given by theta t. So you have this parameter, and then you have this parameter which is the Erding parameter. So it's Langevin. So you are at step t, and then you run a small chain, a small Langevin chain, ni step. It's small because ni will not be very long, and which is Langevin, classical Langevin, plus this quantity, which is theta t minus 1, which reflects the fact that you should be not far from theta t minus 1. And what you do on the central server, you update, you simply make an update. So it's you take this distribution and you update parameter theta t. As I said, it's also Gaussian because it's a product of Gaussian, provided that pi theta is Gaussian, which is the case. So it's Gaussian. So this update is completely explicit. Okay. So basically, you run Langevin on local server, and on the central server, you update the global parameter according to this local parameter zb, which is okay. And then you are willing to do this. You can do analysis. Of course, I will present result only. So we have result for in the non-strongly convex case, but just to explain the result in the strongly convex case. So H1. So you assume that this distribution is mi strongly concave. That there are Lipschitz, of course, it's important that we assume also that the second derivative exists, and we have some parameter gamma I, ni, and rho I. And what you typically do is that you have to control three terms. So you are interested in computing the deviation. If you are interested in computing the deviation of the law of the parameter theta t with respect to the true fusion, so p theta given d, the true distribution. So there are two things. So the first thing is how fast L theta t, the law, approximates the kind of fake distribution that you have introduced, where you have introduced this parameter rho, which is linked with the fact that you have local parameters now. Then you have gamma. So gamma is the step size, and n, which are the number of steps that you are performing at each iteration of Langevin. So then you have a discretization error, how fast this distribution resembles P rho, and then you have the Herding error, which is how far the distribution with the Herding parameter rho is from P theta d. So you have three terms, and then you need to control these three terms, and you can do that, of course. And so at the end of the day, you obtain this type of you obtain this type of control. So you have a first term which is exponentially small, okay, when t which is clear because you it's forgetting of initial condition. All the constants are completely explicit. You have one term which is not very surprising, which is square root of d, square root of gamma, and 1 over rho. So it makes sense in the sense that if you take rho very small, in fact, you constrain a lot, and then it's they try to blow the algorithm. So which means that you should take gamma of the order. So if you want this to be small, you need to take gamma of order rho, in fact, of order square root of rho. Gamma, this should cancel, basically. This should be small. So it means that gamma should be very small. And then, of course, you have an additional term, which is due to the Herding error, which case like rho. So of course, we have, in the constant, we make the D, so the dimension D explicit to understand how the dimension reflects in this distance. So we have a dependence in dimension, which is completely explicit. Okay, we can improve a bit this algorithm, and of course we have found that it's not optimal. So the results which are reported in the paper are not can be improved. So I did not have time to explain, but so if you're interested in this algorithm, you have to wait. I know it would be very difficult to wait until 2 months because we have the time to write all the details. But it's not a mistake, but there is something which is counterintuitive in what we wrote in the bond we had. This is why I will not explain too much. So it doesn't change the algorithm. It changes really the analysis. We had a problem, we were annoyed, but we submit nevertheless because we know that in practice you need in this algorithm you should have bounds which are better and better when you at each local step you run a lot of Langevin step, and in fact we did not have that. So we had a kind of n should be scaled like with function of gamma and rho, which is strange. Hopefully the reviewer did not have it never. So 80 pages. So the way to have a paper in Zurich, 80 pages, nobody reads. Okay. So it's we say in mathematics it's proof by intimidation. So oh, you have 2 hours to read that. Is it okay? Oh yes, it's good. It's good. So and then you put a lot of names: D'Ambrosio, Pierre-Louis Lyons, Villani, so optimal transport, buzzwords. Of course, nobody reads this book, too difficult, but then 80 pages of calculation, people say, okay, that's good, this is very interesting, very well done. And then you have, it's not a mistake, it's not intuitive. We were convinced that there was a problem in the analysis. We fix the problem now, but it's not written yet, but okay. So in fact, you can take n as large as you want. And in this analysis, we had a kind of constraint of n, which was not natural, and of course, which is not there. Okay. So this is why I will not spend too much time there, because you have the n should scale like d, so it's okay. That's not good, and we have this type of analysis, and now it works better than that. Okay, so it works well. So we did many simulation. We drew HPD, high probability high probability region, HDP. So this is it's NIST. In fact, it's NIST. It's NIST with as I said. So when you have 99 in NIST is normal, because if you look at the NIST, there are 4 or 5 which are this one, in fact, basically. So which are, you don't know. So you have some examples which are very strange in NIST. You don't, so it should be a form. So, and so it's so this, you have this. So if you find 100, in fact, you have to worry because it's you have 2 or 3 images which are completely insane. And so basically what you have, so when you see that, in fact, you see that with DGLMC, we have a lot of uncertainty. So it is not clear. So whereas this is you find HTTP, and it's much better. Okay, so we have hyperparameter tuning. So as I said, with this, don't look too much at that because we have, as I said, a kind of optimal. We had a very strange dependence in. So we should have n, which normally, in fact, n can go. N is not limited, so it's not like you can take n as large as you wish. Okay, should be larger than something. Here it should be not too large. Okay, so it's and I think you have so the QR code. I think you have access to the to what? To Git, no? Or,
to archive.
To archive. Okay, so you can okay, so it's prepared by my students. So okay, you can have archive papers. Okay, so takeaway to conclude. So Bayesian certainty quantification. Try to explain why we do that. Of course, Bayesian can be an overkill. This is what I feel now. This is what with Maxime I propose to do. Something else, because if you are only interested in calibration error, I think going Bayesian is perhaps an overkill. And this is also what has been observed, in fact, in this NeurIF competition, that the algorithm which won the competition were not really Bayesian. So it was more ensembling techniques. So for reasons which are not very clear, but it's ensembling technique which won the competition. We have theoretical results which are more or less matched with the results which are done in optimization. We typically need stronger assumption. We introduce 2 algorithms. We have a third one, so which is more federated averaging, but I skip. I did not change this slide, but I skip federated averaging. So we have a kind of equivalent of federated averaging. So this algorithm allow to perform distributed Bayesian inference. They are all theoretically grounded methodology, and they work quite well in practice. So they basically we use methods. So I think this is more or less a closed. So we have problems to fix, but I think there is no much work to do in that direction, at least, because I think we cover more or less everything. But there are many other issues like personalization, for example. There is nothing on Bayesian personalization, so nothing has been done in this direction. So, as I said, so the last technique can be used, but it's not completely a personalized technique. So we plan to work on that with Maxime. Bayesian method is not perhaps the best method to do. If you are interested only in calibration error, perhaps there are simpler methods like conformal prediction and things like that. And that's it. I think I will finish there. And so if you are interested, I have the codes. So the codes are, I think, online. And we have performed a certain number of I did not spend much time on the experiment, but we have done quite a lot of experiments. And especially we will have, so now it's, we have to finish experiment with salad. And, but I think salad is very good technique. So it's like, I think, it's like federated averaging, it's a good technique. So it has one publication for NIPS this year. So I hope it will be accepted.
Okay. Thank you very much, Eric. And if you have any questions, then please ask. And the people who are online, you can write to the chat. I even already see one question. There are several questions, very detailed. So the first question: if we quantize gradients to 1 bit, all magnitude and sign information is lost. Do we really need 32 bits to compute gradients?
That's yes. Yes, that's a very interesting question. So when I say that, of course, you have to be careful that we renormalize. So okay, so first, something which has not been done is that we did not use state through estimator for gradient. So we did not use so we quantized. We can, when we do the quantization, we do the quantization with after. So we perform backpropagation in floating point and then quantize afterwards. But I think, of course, that it would be more interesting to take that into account. So it's a good question, and no, the question is, I believe that it is not a good idea what we do, and we don't have analysis for that, and I never really, I did work on state through estimator, but not in the Bayesian context. I think it works, but I have no idea right now. But I think it's in an interesting direction of research. Yeah. And yes, of course, I agree that it's a kind of overkill to do full precision backpropagation, in particular when you have a very quantized method. Yeah, so you can do better. Yeah.
Thank you. The next question is how acceptable is the performance degradation you observe here? So compared to non-quantized case. Just your opinion.
In fact, quantization does not. So I think quantization. So because you use unbiased quantization, you have to take into account. So this is why there are some kind of compromise. I did not have time to speak about that, because when you hardly quantized and you have an unbiased quantizer, it's a bit like adding additional noise. Okay, and if you remove this noise properly with control variates, and so in fact what you obtain is that you need a much more round, okay, episodes. So there is a kind of compromise which is not completely clear. So either you are doing if you have very hard quantization, so you exchange a very small amount of bits at each round. So what you have the price to pay is that you will converge much slowly, because it's like having a huge amount of noise on top of the gradient. So you need to run it much longer. Okay. So in fact, a direction of research would be something which has not been done or analyzed is that, of course, if you can transmit with high qualities, that typically the number of rounds will be reduced. So if you look at the QSGD paper, so we have something like, so on very small problem diagnosed, we have already 10 to the power 5 episodes. So it's very, very long compared to, so typically for SGD, it's 100 or even less than that. So which means that we pay, the quantization is paid by a super number of episodes. So if you are really interested in the number of bits which have been exchanged, of course, it's not a good idea. Okay, but at the same time, it really depends upon the application, because at the same time, as we said, for example, in cars application, you will use. You have a car which is parked. You use the data which has been acquired on a week. Then this data will disappear. So perhaps it can be very, very long. So it's a different story. So I think we need. So there is. But of course, yes, if you can, quantization is adverse in terms because it adds noise. So it's not a big surprise.
And one more question here, which I also share. So how is it scalable to larger models data sets? So where is the limit here?
So the largest we looked at is CIFAR 100. So
CIFAR 100, but
yeah.
Which type of a model? Like
I think we do a VGG. I need to check, but so it's like no, it's not huge.
Small,
it's not small, but it's not super large model. But it's no, it's not. It's not small. But so the largest we did was because we use a lot of benchmark which has been in the last competition of NeurIP. So it was yeah. So there's a type of benchmark we use at the competition, NeurIP competition, because we had ground truth for this competition.
Okay, I have some more questions from the same person in the chat, but let me first ask to the audience.
It makes sense to consider the brain score as an average function, and valid, I mean, the average function, or maybe something differentiable and
Yes, why not? Yes, it's a bit when you do conformal, it's a bit what you do, basically. So when you do conformal prediction, it's a bit so. If you are, this is why I think Bayesian is a bit too much. If you are only interested in calibration error, okay. So there is even a very simple thing to do, which has been observed by people, is that you change the temperature. So so as you say. So you have a max, you do, if you do the soft max of the decision, okay, and you have the temperature parameter, and you calibrate the temperature parameter on the test set in order for with the Breyer score, for example, you already do 60%, or you do with the one parameter. So I don't remember who did that in I think it's
yeah. It was paper 2014 or something.
Yeah, it's an old paper. So it's an old paper, and it's already, so in fact, for calibration, it's already, it's almost enough. It depends on the task. But on the paper, of course, it was enough. But in fact, it's a bit on advertisement, but it's almost enough, yeah. And conformal prediction is a bit like this, so it's completely different idea. So in fact, Bayesian is providing much more information. Okay, but normally it's providing information. There are many tons of problems behind that. So, and in fact, the problem which is there is that it's completely not obvious to set up the priors. So people use Gaussian priors, but perhaps it's not a good idea. So there are a lot of so it's not obvious to prior selection is not obvious there in general.
Yeah, I have a question that I missed, but when you calculate the gradient, you basically start from one set of values for the weights, but it can be like updated for local model. You calculate for local model, but like global model is already changed. So.
Yeah, so we didn't. That's true. So you can have asynchrony. So here it's like a very yeah, that's perfectly true. So you have to take that into account. So we didn't do that at all. So the fact that for federated averaging, it has for federated learning globally in the optimization context, people have looked at that. So it has been considered that the fact that you have some asynchrony between local models. So typically, one client receive some parameter, compute the gradient, update, but at the same time, the update has already been done. So it was slow to compute the gradient at this point, okay? And the parameter of the global model has already shifted, okay? So then either you drop the gradient, but if you have a very slow client, you will never take that into account, or you correct it a little bit with weights and things like this. So it has. So I did not look in the. I think in Bayesian literature it has never been considered. But of course, in federated learning literature, this type of problem, asynchrony, here it's like perfectly synchronous. Okay. The only thing that we have taken into account, I did not insist on that, but is partial participation. So which means that all clients are not participating at each round. Okay. But we did not look at the problem how to use gradients which have been computed on so the value of the parameter is no longer the good one. So how I use this gradient in order to update my parameter. So this has been addressed in the federated learning literature, but not for I think not for Bayesian setting.
And there was quite small learning rate connected.
Yeah, so the small learning rate is very small. In fact, this is what you use. So it's typical from so even if nothing to do with it's really linked with SGLD. So it's Stochastic Gradient Langevin diffusion. So you typically in most settings, in fact, the learning rate is much smaller than the learning rate that you use for SGLD. So it's not. Otherwise, the bias is. I think it's linked with bias. So it's linked with the bias that you obtain at the end of the day. So typically, you have a small learning rate, and you have to pay, of course, in the number of episodes. Even when you look, it has nothing to do with federated learning. So it's typical from a Bayesian analysis. Yeah. Sorry. No, it's a completely we average like there is no weight, so we simply do averaging. Yeah.
And for each local device, so we use the same type of functions like the revenue rate for each.
Yeah, so yes, that would be an issue as the same that for optimization. So of course, so for federated averaging, typically you can have learning rate which depends upon the proportion. So that's another issue that we did not look. Or of course, when you so typically when the data set are very unbalanced, okay, so you don't use the same gammas for each local user, and of course you should not, when you update, you should take into account the fact that some user might have a much larger variance than the other. So you can do some kinds of, it's linked with data fusion for the fusion parameter. So you typically you need to have a kind of estimate of what is the variance of the gradient of each local user. So you have other hyperparameters to use in this direction.
Like from existing work of federated learning, we assume like all the edge clients has exactly the same model structure. So like I'm wondering, like, are there like research actions to explore? Okay, for each edge client, we have a smaller plot, a smaller model, and then by combining the different outcomes.
That's a good idea. That's a good idea. Yes, that would make sense. Yeah, yeah. I think it has been done. I'm not sure. I did not work on that, but I think it has been done. So which means that you make a global model because by aggregating, so you have each client, each edge client has a simple model because they all look the same, and then of course you make a global model which is because you need more complexity, and so I think it is done, but not in this. I think it's done. So the fact that you have hierarchy of models, yes, it's done definitely. The fact that you use different model, I'm not aware, but I cannot say yes or no. It would be like a random guess. What is your guess?
Because I'm not aware of this kind of work.
Yeah. So we're guessing that there are some hierarchies. So hierarchies that has been done. So hierarchy of edge. So you have, instead of having one authority, you have several authorities, and the several authorities. So the network between authorities change also. So that has been analyzed. The fact that you have different models, and then you have you do a model fusion. So you have smaller networks, and which becomes a larger networks. I'm not aware. Yeah, I think yes, it makes sense. So I think that should be a nice direction. But yes, there are so many other problems to solve for Bayesian. At least we did not look at that yet.
Yes. So you propose to quantize gradient
Yeah.
with the amount of transmitted bits.
Yeah.
Now, if you would really imagine a wireless, full wireless system,
Yeah.
pilots, channel estimation.
Yeah, so no, we didn't look at that. Yeah, so there are some works in this direction. So I think some works have been done by people from this. I don't know which team. So, but Merwan was an author. I know the first paper he wrote when he was here. It was like I don't know who was the author. Obviously, Merwan did not read it, but he's not aware. But but there was a paper. No, there are a lot of literature of federated learning in digital com, where they take into account. So of course you have better channels, or then you quantize less. So I did not look at this. So that's yeah. Yeah. So there are a lot of the techniques, and all these techniques. Of course, if you look at the techniques, which is very efficient for quantization error, so to control quantization error with local step, of course, with the local control variates. In fact, it assumes that you have it's like ADPCM. ADPCM is a complete disaster if you have errors, transmission errors, because you assume that you have a control variate which is updated. The control variate can be updated freely. So there is a control variate on a local device, and this control variate is recomputed from quantized value on the central server. So if you have a transmission error, it's just a nightmare, because then they desynchronize, and you should do something. But yes, that direction of research, you have you have a lot of activities in this direction. Yeah. yeah. Yeah.
If any more questions in the audience, just probably last question from the chat. Can this analysis can be extended to other methods beyond Langevin?
I would say most likely. Yeah, most likely, but I think it's yes, most likely. Yeah. No, at least an adjusted method. So for adjusted method, I don't know because nobody look at that. For an adjusted method, yes, I think underdamped is for sure. If you do overdamped Langevin, you can do underdamped. It will be more painful, but doable. And an adjusted Hamiltonian, which is very closely related to underdamped. Yes, I think it's not so. I think it's much more painful because this one is easy. Underdamped is already much more complicated. And but with if you do now this accept reject locally, I think it has never been done. In fact, yeah. So I'm not sure that it has never been done.
Okay, I think we have no more questions, and let us thank Rick.
And okay.